Hello and welcome to our first half of a lecture on sections 24.1 to 24.4. In this first half of the lecture, we're going to discuss double-slit interference. This is interference from two sources of light. This is going to be our introduction to chapter 24, which is wave optics. This is going to be our chance to explore light through its wave-like properties, or through its very much wave properties. This is lecture 17, and we're covering the textbook Survey 11th edition. Okay, so in this lecture, we're going to have the objectives to recall what happens when two waves coexist in the same place at the same time, and same place and same time, and how this leads to constructive and destructive interference. I mentioned the word recall because this is the exact same properties that you would see with sound waves that is, and that is an idea and a concept that you have seen before in your physics class. We're also going to learn how to understand the interference pattern formed by the interference of two light waves, okay? All right, so with those objectives out of the way, let's get to our key terms. So as I mentioned, we're moving into wave optics. Wave optics is also often physical optics. So we can say that physical optics and wave optics are interchangeable terms. So physical optics, wave optics, and optics obviously implying light, the word optics, is treating light as a wave. Is the study of light as a wave. Okay? And we use physical optics when lengths of our apparati are similar to the wavelength of light. So physical optics is important when optical devices have lengths, it could be any length, similar to the wavelength of light. And that would be, of course, the wavelength of light that we're interested in, because light has a wide range of wavelengths. So if we're talking about visible light, that's going to be in the 350 to 750 nanometer range. So if our optical devices are on that scale, or with really in a factor of 10 of that scale, then we need to use wave optics. So you can think of wave optics, physical optics, as a more careful study of light. So everything that we discussed with mirrors, spherical mirrors, concave and convex, everything we discussed with lenses, converging and diverging lenses, that was all for optical devices that were large. But if we zoomed in on one small part of that optical device, then we may have to concern ourselves with the physical properties of the light and not just treat light as an abstract ray, right? That was a simplification. A simplification which was fine for discussing macroscopic lenses and mirrors, but not fine for discussing very small parts of apparati or small apparati themselves. Okay? So let's then define our next term, which is coherent light. And coherent light is light that all has the same frequency. Okay? So it can be in phase or it could be out of phase. But what we care is that it's light composed of just a single frequency. And we'll treat it as being in phase as well, all right, for our purposes. So this is light that has the same frequency, which would be wavelength in a vacuum. All right, we know that wavelength can change when you pass from one medium to another. But, so this would be all light that when it's passing through, the same medium would all have the same frequency and wavelength, and is in phase. Okay? All right. And we'll discuss phase a little bit more. Obviously, phase is going to be very important when we talk about interference. Phase itself, or light being composed of in phase and out of phase, is going to become more relevant when we discuss something called a polarizer, and that's going to be incoherent light and so on. So we'll get there. We'll kind of get to that that concept. And I guess really there we're talking about unpolarized light and polarized light, but it's a topic that we'll see a little bit more as we continue through chapter 24, but it's not really the main focus. Which we really want to think about is more of path length differences and how that can change phase, and I think I'm going to do a lot of work to illustrate that idea. So don't worry too much, although you are responsible for the definition of coherent light. Mostly, the important thing is that it's just an assumption that we're making. So when we talk about light coming into our very small apparatus, our, on the scale of a wavelength apparatus, then what we want to assume is that that light is coherent. Okay, it's one of our baseline assumptions. Right? Basically, it's like a laser. Right? You think of laser light, it's coherent light because it's all one color, it's in phase. Sunlight would not be. That is inherently incoherent light with all of the different sources reflected off different parts of the sky and the surfaces around you. So overall, kind of natural light in outdoors would be a composition of incoherent light. All right. Okay, so then let's get to our last topic here, and this is another assumption, okay? So parallel ray approximation and small angle approximation. So I just want to get these out of the way as we discuss this idea of the double slit and interfering light, okay? So light from two sources. So the parallel ray approximation gives us the idea that the change in path length for two rays coming through two side-by-side slits is exactly equal to the slit spacing times sine of the angle, okay? So, and the angle being the angle to the location that we're looking at on the screen, okay? Because these slits are going to be lined up and they're going to be illuminating some screen that would be some distance away, okay? And I'll mention the figures that you see on the right-hand side of the screen in just a minute, but let me write down the definition first. So parallel ray approximation gives that the change in path length, delta r, is equal to d sine theta. Okay? Where delta r is, we'll say, difference in path length. And d is slit spacing. Okay, so with the written definition, let's refer to the figures, okay? So we have our two figures over here, right? We got this upper one. Now what's going on with this upper figure? Well, notice we can actually see the screen. So, right, these would be two very small openings. We'll talk about their size much later in the chapter, right? So don't worry about it for now. But for now, we don't really care about the actual width of the opening themselves, but we do care about the distance between them. That's what I call slit spacing. That's d, okay? And that slit spacing is going to be one of the key things that shows up in our formulas. The idea is that these two openings, spaced apart some distance d, effectively make two sources of light. These might as well be two laser beams for our purposes, okay? They're two kind of independent sources of light. And they're going to then continue out into space, right? The space here, and then eventually hit a screen where their effect is going to be registered, right? It could be like a digital sensor or it could literally be a screen. Now, the important thing is that when the light gets there and it hits the screen at some point P, that point P can either be bright or dark or something in between. Why would that be? Well, if we have a bright spot, that's because the two waves arrive in phase. So both the waves are, say, at a crest simultaneously. On the other hand, if we had another spot that was dark, that means one wave arrives at a crest and the other arrives at the trough. So when they arrive at that point, they cancel each other out, just like sound waves can cancel each other out by spatial interference, right? We've seen that idea before. We've seen cancellation of sound waves. So same thing here. Light waves can be canceled exactly the same way, but on just a much smaller scale, right? Because sound waves are relatively long compared to light waves. Not that visible light is all that small, okay? Anyway, so when we continue with this idea, we see that when we draw the picture like this, with the screen relatively close, right, some distance r, big R, from the slits, what we end up with is two paths of different length and a rather complicated discussion of how those paths differ in length. Because we have this triangle, right? It's not a right triangle. And we have to work out exactly what is that path length difference based on R and D, okay? But it turns out that that path length difference can be independent of R if R is really big. So if the distance between the slits and the distance between the screen is quite large, then we don't have to worry about the effect of R on the path length difference. We still need R for knowing the spacing between those bright spots and dark spots, more on that in just a minute, but to find the path length difference, we can find that at least independent of the distance from the slits to the screen. Okay? And why is that? Well, because if R is very large, then our two rays here are two rays that will eventually interfere with each other, either constructively, destructively, or somewhere in between, right? I say rays, of course, they're waves, right? Each of these is composed of a wave that will look like this, right? We're still kind of drawing rays, right? But we're doing that because we're kind of used to drawing rays. But ultimately, those rays are, if we kind of zoomed in on them, they would be a sine wave. Anyway, so these two rays are thought of as being parallel, right? They're parallel. You may be like, well, that can't be the case because they would never actually meet at the same point at the same time and then interfere with each other. But that's the approximation, right? So they're parallel, but they're very small. And it ends up being a good approximation. It gets us results that are really, really close to the actual results, right? So if the distance between the slits in the screen is like a meter, then we're talking a fraction of a percent in terms of error introduced by this approximation. And it does make the math much, much, much easier, okay? So the important thing is then when the rays are parallel, the path length difference between them is simply d sine theta, because you can see it comes from this nice right triangle right here, okay? The right side right there is the 90 degrees. So, wonderful result there, makes it very easy to calculate the path length difference. And the key idea, to jump ahead, of course I'll reiterate this when we get the equations in just a moment, the key idea is that d sine theta, that is going to then, if that d sine theta, that's going to be measured in meters, right? That's a physical distance. If that is equal to, say, half a wavelength, well, what do you got? You got two waves that are half a repetition out of phase, pi radians out of phase, 180 degrees out of phase, however you want to say it, right? In that case, your path length difference, d sine theta, being equal to half a wavelength, what kind of interference is that? Think about it. Bet you know it. What kind of interference is that? Okay, it's destructive. Okay. On the other hand, if the path length difference is equal to an integer multiple of a full wavelength, then they're going to arrive in phase. That's constructive, right? Review the ideas of phase, being in phase, out of phase, from sound, right? Look back at your notes on sound, look back at the textbook section on sound, because that will be a good reminder and it will come back to you. Be like, oh, I have seen this stuff before, right? I highly recommend that. If the ideas of being in phase, out of phase, constructive and destructive interference just don't sound as familiar to you as you would like. Okay. All right, so moving on, we got our other approximation. Let me quickly summarize that. So this is the small angle approximation. So the small angle approximation is a further one. It's a bit more coarse of approximation than the one I just mentioned. And what it allows us to do is treat sine theta as theta, okay? And this comes up in a lot of other aspects of physics, subdisciplines of physics other than just wave optics. The small angle approximation is really crucial when we're talking about pendulums, okay, if that rings a bell. But anyway, what it says is that, it's a mathematical phenomenon, really. So the small angle approximation, but I suppose what isn't, states that sine theta is approximately equal to tangent theta is approximately equal to theta for angles that are less than 15 degrees and measured in radians. So angles smaller than about 15 degrees. Okay, I say degrees there because it's easy to visualize degrees, right? You're like, oh, 15 degrees, that's a, think about 90 degrees, split in half, we got 45, split that in a third, you got, 15, so it's 1/6 of 90 degrees. Oh, okay, that makes sense. I mean, ultimately, if we think of it, then, it's pi over 6, right? Or pi over 12, right? Because 90 degrees is equal to pi over 2, take a 6 of that, you got pi over 12. And they have to be measured in radians, though. And the reason that this approximation only works in radians is because look what we're saying, right? We're literally saying that sine theta, if you plug that into a calculator, is going to give you a value that is equal to theta, like literally numerically equal to it. Well, if your angle is 10, sine theta is never going to give you a value of 10, is it? Right? That's impossible. It's out of the range, out of the range of the results that a sine function can give you. Well, but it works fine in radians, right? Because radians is going to be some small number. It's going to be a decimal less than 1. Well, indeed, then numerically, sine theta and tangent theta and that value in radians will all be numerically equivalent, okay? All right, so the reason I bring up that small angle approximation is because it's going to come up, right? It makes our life easier when we're doing problems like the ones below in the key formulas. Okay, so without further ado, let's look down at those key formulas. Okay, so the key idea here is we're simply dealing with our results. We're dealing with our effects of interference constructively, destructively, right? And so I just simply listed the two cases of constructive interference and destructive interference. Let me label those, right? The bright and dark. Okay, so this one would be the formula of constructive interference. So this would be constructive interference. I know sometimes it seems strange to refer to interference as giving you a bright spot because you think, oh, well, then that's more like they're helping each other out. They're not interfering. But you get the idea, right? Interference is a general term that can refer to both adding something together or canceling something out. And the next one is the destructive one. So destructive interference. All right, and that's that one. All right, so, and the key words there being light and dark, or bright and dark. Okay, so what's the condition for constructive interference? It's simply that their path length difference, because that's what this represents right here. This is the path length difference, d sine theta. There we go. Make it a bit more legible. No, trying to make it more legible. So path length difference by the small angle approximation. Oh, excuse me, by the parallel ray approximation. Path length difference. So if that physical difference is equal to some integer multiple of a full wavelength of our coherent light, right? Our light that just has a single wavelength. Okay, now we could do this for individual wavelengths one at a time, but we can't have light that's composed of a bunch of wavelengths and solve it in one problem, right? This problem is only accessible if we have a single wavelength that we're looking at, right? And so this would just be an integer multiple. We're using m to represent it. So m could be anything between 1 to whatever, right? So integer, and then lambda, of course, is just the wavelength of light. Wavelength of coherent light. Okay, so that would be the condition to get a bright spot on the screen as long as the screen is distant. Okay, you get it. All right, likewise, or very similar-wise, the condition for getting a dark spot where there's fully destructive interference is to have an integer multiple plus a half, because you have to make sure that when the rays arrive, they're always 1/2 wavelength out of phase. So you need to make sure that their path length difference is always equal to an integer plus a half multiple of their wavelength. Okay, so that's all we're saying here. All right, that's why it's m plus 1/2. Okay, and then what's his bottom formula? Well, the bottom refers to the actual distance between the bright spots or light spots. Okay? And let's see. The way I have it written is in terms of integer multiples. So, well, this actually it refers to both. So, excuse me. So distance from center of screen to mth, right? Because it's like the 5th, the 6th, it's the mth bright spot. Now, why would I give you this specific formula? Not give you an equivalent one for the dark spot, because you can think of it as just an example, okay? And why is it from the center of the screen? Well, because the center of the screen is kind of our 0 point. That's the point where the two waves would be arriving with a path length difference that is 0, right? Because you think about it, think about this case up here, right? If I had the two blue rays and they were coming in and they're arriving right in the middle like that, their paths would be identical in length. And when they arrive, of course, they'd have to arrive in phase, so it would be a bright spot. And when they arrive in phase and make a bright spot, then that right there is called the central bright spot, or the central maxima, because it's the maximum, right? It's the brightest intensity, the highest intensity, the maximum intensity. Now, then when we measure things, we measure it from that central bright spot. So we call that kind of our 0, right? That's our M of 0. It's black. So it would be our M of 0 right there, right? And so as we move down, this could, for example, if this was like the second order bright spot right there, right? The very next bright spot, then that would be like an M of 1, for example. So e.g. Okay? And then the distance between that central bright spot and whatever subsequent mth bright spot there is, that is y. So y is measured perpendicular to r and along the screen. Right? And I did this example for the screen here because it's showing, but of course we're really doing it for a screen that's far enough away so we can use the parallel ray approximation. Okay, now what about the small angle approximation? Well, that actually comes up in this formula, so I wanted to mention that. So this formula right here comes from the idea, so we'll say from the fact that d sine theta is equal to m lambda, and d sine theta is also equal to d tangent theta, right? So we can then rewrite it as this. So this would become d tangent theta, because the small angle approximation says the tangent theta and sine theta give us the same value approximately. That would also be equal to m lambda. And then you think about, well, what is tangent theta? Tangent theta, look at the picture, right? Tangent theta is just opposite over adjacent, or y over r, okay? As long as they're parallel rays, right? You can see here, like, the triangles don't exactly match up, right? We got two individual triangles, right? They're slightly different from each other. But we care about this one. And in this case, this distance right here is y over r, opposite over adjacent. So then it just becomes d times y over r equals m lambda. So then if we just solve for y, we get this formula right here, okay? So that is the distance, or the spacing, from the central spot to the mth bright spot. If we wanted the similar formula for the distance from the central spot, the central maxima, to the mth dark spot, we'd simply replace m with m plus 1/2, parenthetically. We could also talk about the distancing between any two bright spots by just measuring it from the center and then measuring the other one from the center and then subtracting the distance between the two. And you can see there's a trend there if you do that. I guess the last thing I'll mention is that this whole idea of treating light as a wave, right, is an interesting idea because we don't necessarily see light as a wave in our everyday lives. And the famous experiment called Young's double-slit interference experiment proved that light was a wave precisely because there was that central bright spot. Because if you think about it, on a macroscopic scale, if we have two pinholes and we have light shining through them, then we get bright spots on a screen that are aligned with those pinholes. But here we're seeing that we get a bright spot that isn't aligned with either pinhole, but is exactly halfway between them, okay? Now, that's only gonna work if our pinholes are really small, right? So, and when we talk about all these spacing experiments, they're all gonna be measured in millimeters or micrometers, right? They're gonna be quite small. So they're going to be, bigger than light, which is hundreds of nanometers, but usually a factor of 10 or a factor of 20 bigger than light, or even closer to a nanometer, right? Especially with kind of microfabrication that we could build this sort of stuff these days. But even 150 years ago, we could make small holes. Okay. All right. So hopefully that all makes sense conceptually, a little bit of history there, and in terms of our equations that we're going to really be working with. All right? These equations right here. Okay. So let's continue on this video a bit more and take a look at least one short example, and then I'll come back with the second half. All right, so let's take a look at example one, kind of put it into practice before we move on. So in example one, I say in a Young's double-slit experiment, right, that being named after the famous original experiment, proved the wave nature of light. Coherent light with a wavelength of 700 nanometers illuminates two slits that are separated by a 0.6 millimeters. Okay, so that's telling us that D, the slit spacing, is 0.16 millimeters. A screen is placed 85 centimeters away from the slits, and using the parallel ray approximation and the small angle approximation, I won't state that every time, I'm just kind of reminding us that is our baseline assumption. What is the distance on the screen between the 8th bright fringe and the central bright fringe? What is the percent error between the distance you found in part A and the distance found not using the small angle approximation? All right, cool. All right. Notice I don't ask for the difference not using the parallel ray approximation. I might make that next week's quiz. I'm going to kind of review, what I want to do. It's a good one. We can actually kind of see how important the parallel ray approximation is, and it definitely gives us good practice with some geometry and some algebra and so on. So that may be it. I just want to make sure there's not another option that I'm missing. Okay, so let's take a look at part A. Okay, so in part A, we can see that it's pretty straightforward. I mean, it was the last equation I mentioned, right? That's the one we're going to use. So I want to use y8, and I'm going to set that equal then simply to, if you look at the formula here, right, r times m lambda over d, okay? So y8 is going to be r times m lambda over d, okay? And in this case, m is 8, okay? So then let's see what we're going to get. So we're still trying to find y8. So I have r, which is given as 85 centimeters. So we'll convert that to meters. We'll plug in our m equals 8. Our lambda is our 700 nanometers. Right, now that we're working with the wave properties of light, we're going to have a lot of things in nanometers. So we get very used to remembering that nanometers are 10 to the negative 9 meters. Right? More legible. Okay, and then that's all going to be divided by the slit spacing d, which was, it's 0.16 millimeter. Millimeters 10 to the negative 3, so I'm going to write it in scientific notation as 1.6 times 10 to the negative 4 meters. So 1.6 times 10 to the negative 4 meters, okay? All right, so we put that all in, and we get 0.0297 meters, okay? If we're rounding it to 2 sig figs, it'd be 3.0 centimeters. Okay, 2 sig figs is kind of what we're working at, as you can see. So it'll be 3.0 centimeters. Okay, I'll leave it like that. So that is our final answer. That is our distance from the central bright spot, the spot that's exactly halfway between the two slits, right? Our m equals 0 location, to the 8th bright spot. And in reality, the 8th bright spot is usually pretty dim because each spot becomes dimmer because it's a greater distance, and intensity falls off as a square of distance. Okay, and so that's sometimes you don't see the 8th bright spot necessarily in a double slit experiment, but we certainly see like the first 4 or so. But if we had a sensitive detector, we could detect it. All right, something more sensitive than the human eye, or maybe just very dark conditions, no ambient light interference. Okay, so what do we get, however, if we don't use the small angle approximation? So we're not going to use that whole business with sine theta equals tangent theta, and then tangent theta just equals y over r. Well, then that means we'd have to actually find theta, okay? So if we're not using the small angle approximation, then we need theta from d sine theta equals m lambda. Okay, so in that case, we'd simply solve for, and I'll call that theta 8 because it's the 8th bright spot. And then that's just going to be sine inverse of 8 times 700 times 10 to the negative 9 meters. Okay, and then that's all going to be over d. Okay, d just being our 1.6 times 10 to the negative 4 meters. Okay, so when we take that inverse sine function, we get 2 degrees. Okay, I'll write out the 3 sig figs, won't be using all of it. So then we need to actually find the, then set up our tangent formula. Okay, so then we've got tangent of that same angle is going to be equal to y8 over r, okay? That's it, okay? That's still a true fact. We're just not saying that tangent theta is equal to sine theta, that's all. So then I would just then solve for y8, okay? So then y8 is just going to be r times tangent theta, which will be 85 centimeters times tangent of 2 degrees, which gives us 0.927. Oh, wow. I guess that small angle approximation was pretty good in this case. Well, because 2 degrees is like great. That's a really small angle, considering that the small angle works up to about 15 pretty well. Okay, and the threshold is being at 15 degrees, or pi over 12 radians, the small angle approximation starts approaching 10% error. Okay, but at this point, it's like tiny. We're talking like, a fraction of 1%, because it's a nonlinear effect between the error. And so we end up, so if we then take the unrounded values and plug them in, our percent error, okay, because I've been running the rounded values here on the screen, the percent error would be, so y8, I'll call that small, that's the one we got up here, minus y8 without the small approximation, divided by y8 without the small approximation, y8 of course being the distance from the middle to the eighth bright spot. That's going to give us, times 100 to make it a percent. That gives us 0.061%. So 0.061% error. Well, I'd call that acceptable. All right. Looks like we can get away with using the small angle approximation in this case. All right. Okay. So there you kind of maybe saw some justification for using one of the approximations. Probably tired of hearing me talk about approximations, but also you just see, kind of see the idea here. How do we actually find these locations? How do we find the location of a bright spot? Well, right, that tends to be what we care about more than the dark spots. Dark spots are just what are between the bright spots, right? Bias of being, light sensitive creatures and all that. So that's how you do it. Okay, that's how it works. Can we always use a small angle approximation? No. Okay, I have some examples where it would be impractical to do that. One case that actually really shows up for when the small angle approximation isn't particularly good is when we're dealing with a very large d, right? So when d starts to be bigger, okay, that's where we start to have, or maybe I'm thinking, no, I think it's when d becomes significantly smaller. All right, so sorry for misspeaking. So when it really starts to get close to the wavelength, if we have a d that's like 1 micron, then we end up having some issues using it. Okay. But I have chosen some examples to highlight that you'll see later. So let's see. I'm going to leave example 2 for practice to kind of follow up, just building off of ideas. So I will wrap up this video with 2 concept questions. I'll come back with a second one where I'll show some more in-depth examples of working with double-slit interference, and then a third video where I introduce another type of interference called thin film interference. All right, so let's wrap up this video with 2 quick concept questions. All right. Now, you can always, if you don't want to, hear the answer to these concept questions and think about them yourself, obviously do so before you listen to this. Okay. So we've got question 1. Light from a point source X contains only blue 395 nanometer and red 690 nanometer components. Okay. So it's light composed of just blue and red light, whatever you get when you mix blue and red. So after passing through a mysterious box, the light falls on a screen. Bright red and blue. I thought I corrected this. I had a version where I had. It's supposed to say bands, right, instead of hands. So let's do that here. Bright. It sounds so funny. Because it's just like not the word you expect to hear there, right? So that's just a typo. So it'd say B, not H. So bands are observed as shown. Right? Can I get away from moving this out? Close enough. Anyway, so what possible optical device could cause this pattern? Okay? Yeah, it's exactly what you think. It's the thing we're talking about. Okay? It is a double slit. That's the optical device that can make a pattern like that. That's it. Okay? Now, could it be more than a double slit? Yeah, it could be something called a diffraction grating, which are a bunch of slits. So it has to be a double slit or multiple slits. Okay? More on the kind of the alternative for now, right? Or later. So a double slit, that would be the optical device. right? So it's an obvious question, but I just wanted to put it in there, right? Make sure that we kind of understand what we're talking about, not lose sight of it. A double device, whoops. So a double slit device. Or multiple slits. And we will talk about multiple slits. We won't kind of go up one at a time and talk about, well, what does a triple slit look like? And what does a quadruple slit look like? Because it ends up being quite complicated mathematically. But we'll talk about kind of the general case where we have hundreds of slits. Okay? Because that's actually quite a thing. It's basically it's called a diffraction grading. It ends up having a particular effect where we have some really well-defined bands. It's what scientists use, astronomers, for finding out the light fingerprint from particular elements, okay? Which is an idea we'll come back to when we talk about atomic physics, and we talk about the idea that we have these electron excitation levels. Well, it turns out that how do we find those electron excitation levels in the first place? We use a diffraction grating. Or we can use a prism, okay? Because how we talked about how prisms disperse light? Well, that's another thing, right? So anyway, and why are they bands like this? Why are the red and blue separated? Well, here the red and blue wouldn't be separated. They'd be on top of each other because they both have a path length difference of 0. So they're both going to allow for constructive interference at the exact same point, the middle point. But that's actually the only point where the constructive interference would be identical or would be located at the same point. Because then as we move on, the locations of constructive interference are going to be a function of the wavelength. I mean, think about the formula that we used, right? When we found the distance, it had lambda in there. So the wavelength, the color of the light, depends or determines how far those subsequent bright fringes are from the central bright spot. Okay? So that means that red light and blue light, which are really on either ends of the rainbow, right? They're the longest and shortest, colors or types of light, respectively, that they would have fringes that definitely wouldn't overlap with each other other than that central one. And so then they get separated. We'd have this distinct, kind of two patterns overlaid on top of each other or side by side with each other. Okay, kind of neat. All right, so question 2. After light from a source passes through two slits, a first-order bright spot is seen on the wall at point P. What distance is equal to the wavelength of the light? Okay. So then, so how do we think about looking at this picture? What distance would be equal to the wavelength of the light? Okay. So how do we relate the information in the figure to the wavelength of the light? Okay. So take a minute and think about it. All right. So if we're looking at the picture, you can see there's distances that are labeled. There's D, there's A, B, and C. Those are your 4 options. Okay. D is just referring to the distance between the slits. B is referring to the hypotenuse of the triangle that's shown there. Okay. Actually, that would be one leg. It's not the hypotenuse. The hypotenuse is D. So B is referring to one leg of the right triangle. The right triangle, right? Here's the right part of the right triangle. And A is referring to the other leg of that right triangle. And then lastly, we have that C is our Y distance. That's actually the distance from the central bright spot to those subsequent bright spots. So which of those is referring to the wavelength? Exactly the wavelength. All right, so you probably got it figured out. It is the extra distance that they have to travel, right? So it is A. So the distance A shown in the figure. Why is it A? Well, because we know that the path length difference is equal to d sine theta equals the m lambda, okay? So the path length difference is this, right? The path length difference is A, the distance A, so the path length difference. But that's equal to m lambda. How can we be sure that m lambda is lambda? Well, because we're told it's the first order, right? That's the terminology. It's the first order bright spot, okay? Because you have the central one, and then the subsequent ones, as we move away, this is the first order. That would be y1, okay? And so since it's y1, m is 1, so that means the path length difference is equal to 1 times lambda. There you go, okay? Path length difference. In this case, is equal to